in the region and in the world. We are here live from Ayuka and in Pune, India, and from Marseille in France. So with us, we have today Mr. Karl Antier, who is avid meteor watcher and a representative of the International Meteorite Organization. Now, there are several of you here who've had experiences watching meteors and watching any other exciting sky phenomenon. And today, especially, we are bringing you this event because the meteor shower, the best meteor shower that I feel is seen from Indian skies, is coming up in about a week. The Geminids, with the kind of the best hourly rate and the best visibility conditions because of winter season. It has been a great favorite of mine, and therefore, for particularly that reason, and not just particularly for that reason that is my favorite, but also because it's one of the best, we bring to you this series of talks, which the theme for which is researching the solar system with the shooting stars. As you know, they're called shooting stars in popular language, and because people kind of mistake them to be stars which are falling down or shooting across the sky. But they are, of course, not stars, and you probably all know the basic backgrounds of what a meteor is and how it's different, very, very, very different from what a star is. So, of course, all this is known to us, and many of you have already had an experience. But sometimes it's also important to change just our experience into an actual observation. Okay, so there is always a difference between just looking at something and loving it and also observing it. So that difference makes you, a step ahead of everyone, and also it contributes a lot of data to science. And I will stress this, that observations from every person in the world about any kind of phenomena that is being observed can make a lot of difference. So therefore, to stress that and to tell you what is the kind of organized way of observing meteors, and also how you can contribute your data, how you can put it in a database, we have with us Karl Antier. So Karl is a geophysicist, and he's worked with a lot of fields, including seismology, and he also does meteor and infrasound. So then he has worked a lot in the regions where geophysicists are required, including mines. He's done geothermy, oil industry, etc. But then he doesn't just look at the ground and work with the ground. He also works with the sky. So basically, we have Karl as a meteor observer for about 22 years. So so we have Karl with us, and he's been gracious enough to give time early morning here, and he's here with his coffee and his talk. So let's not delay further, and I'll pass on the stage to Karl. Please, Karl. Are you muted for some reason? Okay.
Yeah, perfect. Can you hear me?
Yes, please. Thank you.
Okay, that's all right. Just shut up. So good morning or good afternoon, everybody. So we're going to start a small talk about meteors. So as Samir said, it's something which is very easy to observe, that everyone knows, even for the non-astronomers people. And what we're going to see today is just get some basics on the meteor physics, and then to understand after what you can do as an amateur astronomer, what you can do to help science and to make some research on that. Because meteor is a very specific domain which can be observed with naked eye. It's not something you need some big instrument, just like big telescope to observe, or a camera. You can just use your naked eye and just observe with a pencil and make some valuable scientific data. So we're going to see that, because it's something we need you for that. We need everybody in the world to get some meteor science. And so we'll see everything from the beginning until the end. So from the very basics of the meteor until the end, which is making some scientific data, and then make them together, because we got a big network which is called the IMO. So it's the International Meteor Organization, which has been developed 20 years ago to make a big community all over the world to get the data from all the people observing meteors all over the world. Because we need the data from everybody to have a global view of what's happening in the sky in this domain. So that's why you're important for us. And so what we're going to see is that how you can, what you can observe, when can you observe, and what can you give us as a data. And in the end of the talk, you should be able, and next night, you should be observing meteors and sending us data. So I wait for your data for next week. So there's a small presentation that I will share with you, who's going to explain you what a meteor is, because it's very specific domain of the astronomy. It's one which is very easy to get, one which is very easy to observe, one everyone knows, but there are many people who think things on meteors which are wrong. So sometimes it's even astronomers, and there are some very specific things you need to know about meteors to be sure you understand everything. So this is just a rough presentation. For people who know meteors, may be something they know, but for the ones who are not sure of everything, it can be very interesting. So this is dealing with shooting stars, because we use the term meteor, but people usually use shooting star in English, which says that it's a star moving. In the fact, we're going to see it's not a star moving, it's one of the closest astronomical event that we can observe. It's something which is just 100 kilometers or hundreds kilometers of you. So it's very, very close to you. It's something that comes from the solar system, and something that is very interesting for us, because it's the only way we can understand the very, very small particles in the solar system, which is the dust. You cannot make a study of the dust if you do not study meteors. So meteors is the only way we have in astronomy to understand what's happening with dust in the solar system, which is very, very interesting. So we're going to have a look at what a meteor is and what a meteor shower is. So meteor, it's a term that comes from the Greek. So it's European. This is just the only picture with some writings on it. The other ones are very easier to understand. Meteor is coming from the Greek, which means above or in the air, which means everything that is above the ground or which is in the atmosphere, in the air, can be considered a meteor. Most of the time, as astronomers, we think meteor is just a shooting star, but in fact, it's a more global term, which is rainbow is a meteor. We're going to have a look at that. The rain is a meteor. The snow is a meteor. The ice falling from the sky is a meteor. And there are different types of meteors, which is a more global meaning than the one we are usually using. So these three examples, which are snow, and ice coming from the sky, these ones are called some hydrometeors. Comes from the water that comes from the sky. So this is another meteor. This is another kind of meteor, which is the light phenomenon in the sky. So that can be rainbows, that can be the green flash at the end when the sun is setting. This is also a meteor, but it's a light meteor. It's photometeors, this kind of meteor. You can also have some electrical ones. So when you see a lightning, when you see some auroras, when you see like kind of sprites, these ones are also considered meteors because they happen in the atmosphere. It's not a shooting star, but the three ones here are called electrometeors. So these ones are also kind of meteors. And the last kind, there are some others, is the rocky meteors, which is the one where you got a dust or a sandstorm, or you got some small particles in the towns, just like you see on the top left of the screen. These ones are called lithometeors. So all those kinds of meteors are meteors that exist, which we won't study today because it's not our case. But just to be sure you understand, a meteor is something that's happening above the ground in the atmosphere, and it's a very, very global meaning. It's not just a shooting star. The one who is interesting us is this one. So it's what we call shooting star. A scientific term is meteor, and it can happen every night. It can happen anytime. It's something which is really, really nice, can be very, very nice, and it's something that can be unexpected. It's also one of the only phenomenon with auroras, like example in the astronomy, no one is able to predict. In the human history, in the mankind history, we just managed to predict 2 meteors, which were some small asteroids we've been detecting before it enters the atmosphere, but it's the 2 meteors we've been able to predict. All the others, you can raise your eyes to the sky and see one. No one's going to be able to predict it or say, okay, you're going to see something in this. We can have a guess on the activity, which is what we're going to see. So you can have a guess on how active going to be a meteor shower, for example, but you won't be able, even if you know a meteor shower is active, to tell, okay, in 1 second we're going to see a meteor, which is not the case for eclipse, for any other phenomenon. And what makes this phenomenon very specific in the astronomy, it's not predictable, or not too much predictable. So we're going to see that now. Because a meteor is, as we said, it's made to, it's dust. It's a way to understand dust. And you can't see dust with a telescope. You can't see dust with a radio telescope when it's in the solar system. You can only see it when it enters the atmosphere. You've got many dust in the solar system. There are two examples that allows you to see it. It's when you see the zodiacal light. So it's some kind of light you see above the horizon on the west when the sun sets, after the sun sets, and on the east when the sun is going to rise. So this is the light of the sun which reflects on the dust. And that makes this kind of cone, light cone shape, which is called zodiacal light. So that's a way to see there is some dust in the solar system. Another kind of dust you can see on the right part of the screen, it's a comet. And you see that before and after the comet, there's a kind of ray of light, and this ray of light is the dust that's been released from the comet. So you can have a look at where it's located in the solar system. You can see exactly where it is, but you won't see the dust particles individually. The only way to observe them is to watch meteors. And this dust, when it enters the atmosphere of the Earth, it's something that comes very, very fast, because dust is very small. It's kind of below the millimeter diameter. When you see a shooting star, you must remember the phenomenon which you see is due to something which is smaller than a sand grain entering the atmosphere. It's very, very, very small. But it goes very fast, because the Earth is rotating the sun at 30 kilometers per second. A particle which is in the Earth environment can go between 0 kilometers per second until 42 kilometers per second. If it goes faster, that would mean it does not belong to the solar system. So most of the time, 99.999% of the time, it's something that does not go faster than 42 kilometers per second in the Earth environment, which makes that if the rocky or the dust is coming below the Earth at the same speed of the Earth, we should say, okay, it will never catch the Earth, so it will follow it and will never hit it. It's not the case, because the Earth is attracting. Due to gravity, it's going to attract the dust, and so the dust will be accelerated. And when it's accelerated, it's going to be accelerated to 12 kilometers per second. So the slowest meteor you will see is due to a dust arriving at 12 kilometers per second. That's the slowest meteor you'll see. The fastest one is going to arrive in the opposite direction at the fastest speed existing, so 42 kilometers per second. So that's a direct collision shock, and that makes meteors coming at 72 kilometers per second. So that means a meteor is a dust grain which enters the atmosphere between 12 and 72 kilometers per second. And it's this speed that makes it light. Because when you see a dust grain, which is 100 kilometers, even if you burn it, you will never see it. So what you see when you see a meteor shooting star coming in the air, it's just a dust entering very, very fast in the atmosphere. And when it enters the atmosphere, it's make ionization of the atmosphere. What you see is never the grain which is melting, the grain which is in fire. It's just the atmosphere that becomes light. It's the light that emits the atmosphere on the path of the dust grain. So it's very important, because that means you will never see the object itself. You will see some direct phenomenon that are linked to it, but you will never, even for big ones. If you think of Chelyabinsk, was something like 15 meters diameter when it enters the atmosphere. It's the biggest meteor we've seen for the last century. Even if you take a rock which is 15-meter diameter, if you put it 100 kilometers from you, you will never see it directly. So that means when you see some videos of Chelyabinsk entry, it's not the direct rock you see, it's just the indirect phenomena that you see. So this is the explanation of why we see meteors, is that it's a small particle that goes very, very, very fast. This is another point of view to watch meteors. When you see from the ground for years and centuries and millenniums, no one knows exactly what it was. If it was in the space, if it was in the atmosphere, and what was the phenomenon itself. And even when you see a shooting star, sometimes you're very surprised of what you really see. Just what I said, that you never see directly the dust is something really interesting, because most of the time people think, they tell us, they say, okay, I've seen a rock in fire coming in the sky. You never see a rock in fire for many, many reasons. And when you see from the ISS, so this picture was taken from the ISS, you see on above how a meteor looks like. And you see it's really something happening in the atmosphere, in the high atmosphere. So most of the time, meteors, when you see them, they are between 120 and 80-kilometer altitude. So it's very high in the sky. And that explains that even if sometimes you got the impression it's very close to you, because your brain is not that easy to use in the night, is when it sees something that goes fast and is bright, it thinks it's very close, and sometimes it thinks it's close to hundreds of meters. People sometimes tell us, okay, we saw a meteor falling in the garden of the neighbors. It's not the case. When you see a meteor, it's at least 100 kilometers from you. And this picture really shows that, is that a meteor is something which is very high in altitude, and it's something which is seen by many people at the same time. For a country like mine, which is France, you can have some meteors which are seen from all over the countries. When it's very high in the atmosphere, if the skies are very clear, there can be some shooting star that can be visible for everybody in the country. For India, it's a bit wider, so I guess maybe not the whole country will see it, but you can have some meteors which are visible for 1/3 of the country, because it's high in the atmosphere, so many people can see the same phenomenon. It's not going to be happening in the same part of the sky, so some people will see east, some others will see it west, but it's going to be the same phenomenon. And it's interesting for you, because you can make some studies just on one meteor. So this really shows you what it looks like when you see a meteor from above. And when you look closely, you really see the path, you see the atmosphere, you got to guess that it's really lost in the atmosphere, and it's the case. And on this path, there was a dust sun, a grain of dust entering the atmosphere. This is a meteor. So this, just to make it sure everybody got the good terms, because even scientists, even journalists make the mistake. There are some different terms that deals with meteor. There's one which is meteor, you know it. There's one which is meteorite, and I just said a few minutes ago meteoroid. So these are different terms that do not refer to the same date in the life of a meteor or the life of a rock. The meteorite, shooting star, asteroid, and you've got meteorites too. So this one is a meteor. This small rock falling on the ground, this is a meteorite, and it's completely different. A meteor is this light phenomenon you see. So it's called the shooting star. It's the second definition you see on the screen. A meteor is just a streak of light in the sky. That's all. It's not the rock. It's not a rock on the ground. It's not a rock in space. It's just a streak of light. So when you see a shooting star, you see a meteor. If you go out and you find a rock on the ground, which you think comes from the space, it's a meteorite. But it's a completely different domain than meteor. Meteor is really the study of shooting star. Meteorite is a rock that is on the ground. And before it enters the atmosphere, this rock is an asteroid if it's very big, and it's going to be a meteoroid if it's small. So when you see you got some dust or some grain particle that comes to the Earth, it's called dust, space dust, or meteoroid. The meteor is the light phenomenon, and the last one, meteorite, is the rock you may find on the ground if the meteorite is very, very big. This is meteors. These are shooting stars. And it's just an example, because we see that to get a meteor, we need an atmosphere for the dust to enter at high speed, and we need a dust particle. So there's another planet in the solar system that can give some meteors, and it's Mars. And we've been recording a meteor on Mars because we got nearly the same conditions. The atmosphere is not as dense as on the Earth, but you have to know that on Mars you can have some meteor. You can have some meteor showers. There was some prediction meteor showers on Mars. And this one is an example of a meteor that's been taken by opportunity when it was looking at the sky. So you can have some meteors on other planets than just the Earth. So this is just the basics on meteors. Now what we're going to see what a meteor shower is. The Geminids, which is going to happen in 1 week, are meteor showers. Meteor showers is maybe not a term that is very, very easy to understand. That just means we're going to have some meteors coming from space, some meteoroid, some clouds, particle clouds, which come from the same region, which comes from the same origin. So they're going to have some characteristics which are similar. And this makes what we call a meteor shower. Gemini is a meteor shower. Perseid is a meteor shower. We've got some thousands of meteor showers. Some are very active, some are not. And we're going to see the more active ones. Just for remember, the solar system, it's 1 star, 8 planets, dwarf planets, and many other big stuffs. And there are also some small ones, just like asteroids, which are most of them between Mars and Jupiter. And you got also, this is a picture of the asteroids, the one we managed to picture. And you have got the comets. And these two small objects, the asteroid and the comet, will be the most big particle feeder of the solar system. Most of the particles comes from the comets and some of that from the asteroids. This is some comet nucleus. So what you see is that's just kind of icy and rocky stuff. And a comet is something that is really interesting, that it melts when it comes from the sun. And what you're going to see, if we make a simulation, is that you've got the Earth on the bottom right, you've got the sun, and the comet orbiting the sun. So these three objects are going to make something completely crazy when the comet is out of the sun. So it's when it's far away, it's just some icy and rocky stuff. So it's gonna behave just like an asteroid. It's nothing special. And when you observe it with a telescope, you just see with the arrows, it just looks like a dot, which means it's just like a nucleus. It's not very interesting for us for the moment. But what's interesting is that it comes from the outer part of the solar system. That means it's very cold. So it's icy and very cold. And when it goes closer to the sun, the ice which is in the nucleus is going to start melting. And when it starts melting, that brings with the ice the dust. Because comet is ice and dust. When the ice melts, it brings out the dust with it. So when the comet starts melting, you see here you got some rays. These rays are the ice which becomes gas when it's going to get hot. And at the same time, it emits particles in space, which are the dust which was inside the ice. And this is very interesting for us, because that means a comet, when it comes close to the sun, is going to release some dust particles. And these dust particles, if they are at a good position at a good time, can enter the atmosphere and make a meteor. So this, when the comet is very close, that makes something very nice like this, like what we had this summer, which is a nice comet. And what you see on the left picture is the comet Chury. So you see all the ice melting with the dust coming with it. And on the right is how it looks like from the Earth. And what you see in blue is the gas which is emitted by the comet. And in white, what you have is the dust particles. So all the dust particles are particles that you can imagine making a shooting star if one day we met them. So when you see a big comet, you see there are many, many particles emitted by the comet. So when we enter such a cloud, it makes the same phenomenon than when you drive under the rain or when we drive under the heavy snow. It's just when you enter such a cloud, you will have the impression in your car that all the is when you add the speed of your car and the speed of the rain, it's the melt. It comes from this point. You got the impression that every particle from one point. This point in astronomy is called the radiant. You've got exactly the same phenomenon in the car than with the shooting star. When we enter a dust cloud, which come from the same region of the sky with the same origin, we have the same phenomenon we have with the rain or the snow. We'll have the impression, and it's just an impression. They do not come from one point. They are all moving parallel because they got the same orbits. And we have the impression that they come from one point of the sky. And this point is called the radiant. For the Geminids, the radiant is in Gemini. That's why it's called the Gemini. For the Perseid in summer, it comes from Perseus. And we'll see that for the Leonids that occurred a few weeks ago, it comes from the constellation of Leo. So that's how we name the different meteor showers. But this is just the parent. They do not come from one point. It's just the way they appear in the sky when they belong to the same meteor shower. For example, this one is another picture with some meteors that belongs to the same meteor shower. When we look at the point they come from, it's in Perseus. So these shooting stars are Perseids. And this one here, it's coming from, if you look closely at it, it comes from a place that with no real easy constellation, it's the Quadrantids. So it's a meteor shower, the biggest one of the year, which happens in January and which come from a lost constellation. It's not existing anymore, but it keeps the name of Quadrantid. This is just a summary of the three big meteor showers. So the Perseid, I guess you know, it's in summer. It's one of the most known in Europe. I don't know for India, but in Europe it's well known because it's in summer when people are on holidays. So everybody knows the Perseid. It's called the summer shooting stars. And it's not the more active ones, because we got some specific characteristic we can have on meteor showers. The first is the activity dates. So the first Perseids can be seen at the mid-July until the end of August. The maximum is around 12, 13 August. And the ZHR, this figure is very interesting because it gives the activity rate of the meteor shower. 110 means if you are under perfect conditions, which means no clouds, no lights, no moon, no light pollution, and the radiant on top and the zenith of the sky, then you can observe 110 meteors per hour. Under these conditions, most of the time you don't have them, so you see less meteors than what this figure gives, but that gives you a rough idea of how much meteor you can see in a night when you got your parameters. The Geminis, I won't be long on that because you're gonna have a presentation on that next week, and it's gonna be observable next week. They are active on a smaller periods, but the ZHR is higher than the Perseids, and it's going higher and higher. So if you survive in the 115 and even 200 years coming, the activity is gonna rise for 200 years. So that means if you observe meteors, or your children and little children observe Geminids in 100 and 150 years, they're gonna have something like 200 ZHR. And so the radiance in Gemini, and one specificity of this meteor shower is if it comes from an asteroid, or at least it's an extinct comet. And the last big one is in January. We've just speaking of that a few minutes ago. It's not very easy to observe because the radiance is not at a good position in the sky. You can just observe it for a few hours before the sunrise, but it's one of the more active of the year. So it's between 90 and 120 meteor per hour as a ZHR. So these are the three biggest meteor showers, but you have to know that there are hundreds of them, and some are just 2 meteor per hour, but we know they got the same origin. So when we observe some, when it's very active, it's very easy to observe because you see many meteors in different parts of the sky and you can easily see the radiance. When you got some meteor showers, which are as interesting, scientifically, they are as interesting as the big ones. You may see 1 meteor per hour or maybe 2. And when you look at the apparent path, you realize they will come from the same place of the sky. So that means they belong to the same origin. And these very small meteor showers, they are not easy to observe to start, but they are very interesting for us to understand because it's one of the most interesting thing we have and we need to understand. So I'll be very fast on that because I want to show you just after the IMO website to show what can be interesting for you. Why is it interesting to study shooting stars? It's for many reasons. The first one is that it's the only way, as I said, to understand what's happening with very small, tiny particles in the solar system. You can observe the planets with telescopes. You can observe the asteroids with telescopes. You can observe the comets with telescopes. You can observe the many small things. You can observe the TNOs. You can observe the dwarf planet with telescopes. It's no problem. But you won't be able to observe and study dust from the Earth without meteors. So it's the only way we have today to understand how the dust behave in the solar system, how it evolves with the gravitational, non-gravitational forces, and it's the only way we have to study dust, but we have to be no, it's not to be sure. I miss a word. You have to understand that it's the dust we study is just the dust in the Earth region. We won't be able to study dust in Jupiter, Saturn, or Uranus environment. We can only have a guess on how it's happening around the Earth because we don't be able to. We do not see shooting stars that many on Uranus or Neptune. It's also the only way we have to start predicting them more and more accurately the meteor storms, because we've been speaking of meteor showers. Meteor showers is what you see every day, but some meteor showers have some non-very stable activity, just like the Leonids in November. If you watch at them a few weeks ago, it was only ZH era was just 20 meteor per hour. If you came back 20 years ago, that was 3,000 meteor per hour. So it's a kind of meteor shower which is not very regular, which can have some very big activity and low one. And we want to predict more and more correctly them. So some are very well known, just like the Leonids. We got some very big fiascos at the end of the 19th, 20th century. So we started predicting more and more correctly. There are some which we are not able to predict today. So the more we're going to observe them, the more we're going to be able to predict the future meteor storms. So that's very interesting for us, for the predictions, and for even for our understanding of how a particle behaves between the time it's emitted from a comet nucleus until it enters the atmosphere. So this is meteor storm. I'm going to be very fast on that. You will find many data, many things on that. That was the Leonids, which is one of the most famous producing meteor storms, but it's not the only one. There are many other ones. Draconids do, and some other meteors make some outbursts. So this one, it's just a reminding of what happened in 1998. That was a revolution in astronomy, which means when you watch at the Leonids, every time the comet that give birth to the Leonids come close to the Earth, come close to the sun, that makes a meteor storm. And in 1998, the Earth was passing the dust cloud just a few days before the comet will pass. So we had a guess there's going to be a huge meteor storm because the comet was passing and we were passing the dust cloud just before. So we thought we would see maybe the biggest meteor storm we never observed, and that was absolutely not the case. There was some prediction that would happen in Asia for you, and people who was traveling from Europe to Asia, but they got a much better show in Europe than in Asia, where there was no meteor storm. That was the time we realized we were absolutely not understanding what was happening with meteor showers. So that was hope, but there was a fiasco, and then we make some predictions. So there was two researchers who said, okay, so they were very, very courageous because in 98, everybody said, okay, astronomers do not understand what's happening with meteors. They predicted the storm and it did not happen. So we lost all our reputation. And a few months later, researchers said, they were David Asher and Rob McNaughton, and they said, okay, we predict a storm in 1999, so next year, they will occur on that date and on that time with 1 minute, they said 2 hour, 8 minute UT. So that means they predicted 1 minute precision, and we were not able in 1998 to predict something at 1 day or 1 year. So that was very, very courageous, and it worked because it happened. And what they realized is that when the comet is passing close to the sun, it releases a dust cloud, which is very, very tiny. If you go out of this dust cloud, you won't see a storm. If you enter it, you'll see a storm. And they realized that in 1999, we were entering one of these clouds, and we had a meteor storm. That was the prediction. So 2 hour, 8 minute UT, and it happened 2 hour, 02 minute UT. So it happened at the time, at the prediction. It was the first time we managed to predict a meteor storm with a minute range precision. So that was a big revolution. And that helps us to protect satellites and astronauts, because there's dust particles. So when you are on Earth, there's no worry for you because you won't be hit by a meteorite. But what can happen for satellites and astronauts is that they are not protected for that. So when you got a meteor storm, so that means there are many particles and dust particles coming very fast. So if you got a strategic satellite which is directed in the path of the dust, it can enter the satellite and break it or make some electrical damage in it. Or if you got an astronaut, it's even worse. It can make a hole in your in your shoe. So that means you will die. So this is one of the. It's not a direct, but we've been protecting Hubble telescope a few years ago to be sure the mirror was not directed in the direction the meteor was the dust particle were coming from for Leonid dust storm. So we can protect some stuff and some people with this prediction. So that's why we need to get them. So it's a nice show when you're on the Earth. It's a deadly one when you are out of the atmosphere. So that's one of the way we can protect some equipment and some people. So that's why it's interesting for us to study them too. It's more interesting. And so we can also study some comet we never saw. Because we know some meteor showers are related to a comet, we know, but we see some meteor showers which we see some activity, but we are not able to tell today which meteor it's linked to. So that means we can have some meteor showers which come from comets, which come back to close to the Earth every 1,000 years or 10,000 years. So that means if one day we see a new meteor shower coming, which we never observed before, that can say, okay, there's a comet coming, we don't know. And what's good is that if dust particles can enter the atmosphere, that means the comet has an orbit which is coming close to the Earth. So that means one of the deadly danger of the collision. So that means comet that makes particles that makes meteors are comet that are potential impactors one day. And if we don't know them, we cannot be sure we can predict something. So today with meteors, we can imagine one day we'll be able to know a deadly comet's coming because we see some meteors linked to it arriving before the comet does. So that's some example of what you know, I guess, of impacts on the Earth and on Jupiter. And one last point for the meteors, it's the meteor recovery, which means if you see a very big shooting stars, that means the rock that enters the atmosphere was big, and that means maybe some parts been surviving, and these surviving parts are called meteorites. And for example, and that's one of the points that's going to be linked with what we will say a few minutes later, is that when you see a big meteor, you can make a report on the IMO website. And combining this report, we are able to trace back the trajectory, the atmospheric path of the meteor in the atmosphere, and then get the potential landing zone, and then get some meteorites. And in January 24, 2016, that was one of the first time we get some reports coming from Florida in the US, and we were able to find a meteorite directly linked to these. There was nearly no videos, recordings, just visual reports, and we were able to find back the meteorite that gives birth to these meteors. This was it. So that's why it's important to observe meteor showers to get some activity. It's also important to get to observe and report fireballs. It's the name of the big bright meteors, because it can help us to get some meteorites back. So this is small it's not that small, but it's a big presentation of the meteors and meteor showers and why you should now start observing it. Just before we take the questions, I will just show you the IMO website, because I guess it's going to be interesting for you. This is the IMO website. It's interesting for you because it's going to show you the last news regarding meteors. So when there's a big fireball that's been happening, then you will have some guess on where it happened and what's the result of the. I'm just sharing at the same time. My brain is just monotask, so I'm not able to make everything at the same time. So this is the IMO website interface. You're gonna see, because we don't have that good network in southeastern France, so we see it's downloading at the same time. So you see there are some last news dating from a week ago about bright fireball. So you will have some information on the last bright fireball that's been observed. You will have information about the future meteor shower activity. So whether for the regular one, just like the Geminis, we should make a post last week about the Geminis and to give some Gemini observation tips to help you observing it. You will also have there's a paper which is edited by the IMO, which is called WGN. So if you're a member of the IMO, you can have an access to it. And you see there's some tips to observe the Leonids this year. And you've got all the global information about the IMO here and the meteor activity in general. There's a 1-year conference cycle, which was not made this year due to the COVID-19. So every year, all the researchers, all the amateur astronomers, because there's a very, very big community of amateur astronomers, and there's a very big link between amateur and professionals. Because professionals won't be able to observe meteors, but they need the data. And the only person that can give the data is the amateur. So there's a very big link between amateur and professional, which when you see a paper on meteors, most of the time you got as many authors which are amateur than that are professional. And in this type of conference, you will meet much more amateur astronomers than professional ones, because the amateur are observing and they need to observe properly to be sure that data will be useful. So this is the conference cycle we have. And what you will see here, because it's also the place you'll be able to report your meteor observations, or you can even download the data, because everything is available. All the data that's been recorded by the organization since its beginning in 1988 are available on the website. You can have a guess on that. When you see here, you've got an activity curve of the Leonids. So this is done with the observation that's been made this year. And you can have a guess here. If you observe a fireball, a very big one, a very big meteor, you just go here, add an observation, a report fireball, sorry. You click on it and you got an online fireball report form, which is very easy to fill in. If one day you observe a meteor, it's a very good start with meteor. And then we combine all the different observations from the different people, and we can have a guess on the trajectory of the meteor. So that's very interesting for us, and it's available in many languages. You can have it in French. You can have it in, I guess, in Indian. It should be available. I think something like 40 different languages availability. You can have here. You got English. And I don't speak that good Indian, so I don't know if it's available in Indian, but it could be available in Indian. So, and if it's not, if you want to make a translation, we are very happy to get it. So if you want to do it, you can. And so this is one of the easy way to make some meteor data. And the last one is when you observe a meteor shower. So when you're going to observe the Geminis, what we like to have is to have like an activity curve like this one on the Leonid on the right of the screen. And these light curves can only be done with your observation of the meteor, but more generally than just one shooting star. So that means when you want to make an observation, you need to record many parameters on the state of your sky, if it's cloudy, if it's polluted, because if you see two meteors, but your sky is very bad, that does not mean there's no activity. That means there may be some high activity, but due to your local condition, you are not able to observe everything. And so we need to get some parameters of your sky to make some corrections. And when you observe meteors, you need to record all the meteors you observe to be sure of their path, their apparent path, to guess if they are really belonging to the Leonids or the Geminids. As we see, when a Geminid is coming, it seems to come from Gemini. So if you see a meteor, even if it's during the Geminid maximum night, and it does not come from its trajectory, it does not come from Gemini, it's not a Geminid. It's just a sporadic one, maybe something that was just in space, or it belongs to another meteor storms. So the first thing you see when you see a meteor is just checking if it comes from the good point in the sky. And after that, you've got some other parameters to record, just like the brightness with the magnitude, the apparent speed, to be sure it belongs to the Geminid, because every meteor storm got its different atmospheric entry between 20 kilometers per second to 72 kilometers per second. And that makes some more or less high-speed meteors. And the color and fragmentation, every parameter that you think is interesting for us. So you record everything on the meteor you observe, and after that, we are able to make an activity curve and also a dust particle analysis, because the brighter is the bigger. And you will see for the Geminis, if you got the luck to observe it on different nights, you will see that the meteors are sometimes more bright, sometimes less bright, and it's not something that is completely random. You will see there's a real evolution of the brightness of the Geminids before and after the peaks. I guess Bob will tell you, or it's Peter Janiskens, maybe making the conference next week, but you will see one of them. They will explain you, but you've got a dust size repartition before and after the peak for the Geminis. And it's very interesting for us because that shows the dust is not behaving the same when it's very small and when it's big. It's pushed more or less by the sun, and that makes a real arrangement of the dust particle. And if we do not observe meteors, we're not able to understand that, and to observe it, to understand, and to explain it. So that's one of the examples of why it's so important that you start observing meteors. And all the data, if you're interested, and if you don't want to observe, but you just want to get the data, it's here. If you go to resources here, you will have some meteor softwares. You can have some VMDB, is a virtual meteor database. You will find all the observations that's been made since the beginning of the organization available here. And you can draw some activity curves for Geminis. We can have a look. You just click on resources, live ZHR, and we can have a look at the last Geminid activity curve for like Geminid into, I don't know, last year was good. And you can have a guess and have a look at how it behaves in the previous years. That was not, depending on the years, if there was some good moon condition or not, you can have many data or you can have nearly known. It really depends on the activity. So last year was not that good because you see you don't have that much good coverage, and we got some very lack of information, especially when it's night on the Pacific Ocean, because it's a place where there are no people observing. So most of the time we got some lacks when the night is above Pacific or things which are not very populated. But this is the kind of data we can have from your observation when you send them to us. Okay. I think I'm okay with the presentation, which was a bit long, but if you have any question, just ask them now, and I'll try to answer them as much as I can, if you're okay with that. And there are many other things to say. So if you have some question that you raise in 1 week, 1 day, or whenever, you just ask them, please. We'll be very happy to answer. I will stop sharing, maybe. Okay.
Thanks, Karl. That was lovely and
Welcome.
a good summary of all the things. And I request everybody not to switch on their videos because I can see that whether you're sleeping or eating, etc. Thank you very much. So yeah, it's been a good introductory session, and thanks for reminding our audiences that the next meteor shower is coming up right away next weekend. So they should get all the sleep in the morning and be ready for the nights.
Yeah.
Yes, of course. And so there are also a lot of questions coming in through the chat. And like you, I'm also trying to multitask here with the chat box here. So a lovely audience, lovely questions. And I will first take some questions basically about meteor showers themselves. So what are meteors and things like that. So let me begin with that. So Sanjay is asking, what are the kind of size range of meteors that are there? I mean,
the size of the dust particle that gives birth to the meteor, or the size of the meteor itself?
That's right. So there are some questions about meteors and what kind of, I think there are meteorites. So I'm not sure whether Sanjay is asking about meteorites, but if you could answer both, then it would finish.
So size of particles, most of the meteors, 90%, 95% of the meteors are smaller than a dust grain, sand grain. So it's very, very small. It's below the millimeter diameter. When you see a fireball is something, it's a meteor that is brighter than the brightest planet. So most of the time we say if it's below magnitude -4, it's called what is a fireball. A fireball, which is the brightness of Venus, -4, is something that is millimeter sized. Something which is as bright as the full moon can be something which is tens of centimeter diameter, just like a small ball like this. And so it's not very big, it's the size of a ball. That makes a meteor which is as bright as the full moon, just to give an example. Right. So when you see something very bright, it's not necessarily very big because you, as we said, it's very fast. And depending on the speed of the meteoroid when it enters, it won't send the same light. If you take this kind of ball, if it goes 12 kilometers per second, it's going to make something maybe magnitude -8. If it goes 72 kilometers per second, it's going to be very fast, but it will make something -12. So depending on the size, on the speed, on many parameters, you can have different magnitude of the meteor depending on the same size. So the smallest is smaller than dust grain, it's millimeter, micrometer. The biggest one, when it's full moon light, brightness is something like the size of a small ball. And the meteor itself, it's very complicated to know because the light path, the real light path, so the luminous one, it's just like a big tube, a big light tube. We get something which must be tens of meter diameter when the meteor is passing. So that means the atmosphere is becoming bright on tens meter diameter tube. And when you see a very bright meteor, you will see that it's not the rock which is light. It's really the atmosphere, because sometimes the atmosphere remains bright for a few seconds and sometimes even a few minutes. And then you see that it's moving in the atmosphere depending on the high altitude winds. You see the what we call a persistent train, and it's moving depending on the wind. So that really shows the light phenomenon is not the rock itself, it's really the atmosphere.
Lovely.
I don't know if you answered the question.
Yeah, so I think there was another question about the same thing that they've seen by Sarath, that they have seen a trail of the meteor and then it was hanging there like a cloud for a while.
It can last. Last winter, there was one which was photographed from France. It lasted 40 minutes.
Wow.
So most of the time with naked eye, for the bright one, you see it for seconds, maybe minutes, but sometimes when you picture it and it's even visually visible, it can last for tens of minutes. It can be very long.
Sure. So that's a good point you make, Karl, that meteors are mostly the atmosphere making its presence felt. Yes, it's really good. So there's a question from Tanish that if all these meteors are coming through the atmosphere and burning up there or diffusing, then are they causing a change in the atmosphere? And also, are they causing a change in the Earth's composition?
Yeah, that's an excellent question, because it makes change. Because another good point is that the rock is not burning; it's melting, it's sublimating. That means just the surface of the rock will melt. Inside the rock, it's still very cold, because in the space it's very, very cold. So the deepest part of a meteorite is very cold, and just the surface is melting. So that means it becomes nearly gas at the same time, or very small particles. And these very small particles, even for small meteors, make micrometeorites. So when it's very big, the big rocks fall on the ground. When it's small, just like dust grains, it melts and it makes some very small rocky drops. And this one remains in the atmosphere for years, for months, before the rain makes them go down, the gravity makes them go down, and if sometimes they go down, but they can remain in the atmosphere for years, tens of years. We don't have a real guess on that. We don't know. We can make some models, but we are not 100% sure. So this is, you can imagine that you've got some dust, space dust everywhere in the atmosphere. You can collect them when it rains. You just get the rain, you make it vapor, and then you get some rocky metallic stuff. And if you look at with a microscope, you can have some very small meteorite particles. And what's good is that it makes some very small particles in the high atmosphere. And maybe you've been hearing about the noctilucent clouds, which are very, very high altitude clouds, which are between 100 and between 80 and 120 kilometer altitude. And we have a guess that these clouds can form because there are some meteoric particles at this altitude. So you cannot make a drop of water in the atmosphere if there's no real particle that allows to make the drop. And the only way to make clouds at this high altitude is to get some meteorites particles that allows the drop to form and then to make the clouds. So it's got some influence on some atmospheric phenomena, just like these clouds, but there's no influence on, I don't know, global warming and things like that. But you can have nucleus cloud. If you look at on the internet, it's very high altitude clouds, which are visible when the night is very dark. So it's interesting because you're in the real dark and you got just like a ghost light coming from the north most of the time, but you're a bit south to observe that. But yeah, so it's clouds which are very high in altitude, so there is still reflecting light of the sun, even if the night is dark in your place. And these clouds come from meteors, we guess, meteor particles.
Great, excellent. So, there's a question. I think it got answered here, but the question was very interesting, so I'll still read it out. So I think Shrisha was asking whether if we could eject some small rocks into dark space, I mean, in the top atmosphere at 40 to 70 kilometers per hour, would they create the light streaks just like space dust? Yeah. So
yeah, because there was some very strange ideas, but for the Olympic Games in China, there was a project to release some dust in the space and let them enter the atmosphere just above where the Olympic Games were happening, to make a fake, not a fake, but an artificial meteor storm. So it's possible, you can do that. Wow. It's very expensive, but you can do that. But it will make, what the big difference between this kind of meteor storm or meteor shower and the real ones is that if you go into orbit of the Earth and release some dust, it won't go as fast as the real dust particles. Because when you see a satellite re-entry, most of the time it's something like 8 kilometers per second. So if you release some dust from space, from the neighboring of the Earth, the speed of the meteoroids won't be as fast as the real ones. So it will make some very slow meteors. It's the only difference.
Okay, that's interesting. It's very interesting to know.
So if you see a meteor, if you want to know if it's a fake or not, you just see the speed. If it's less than 12 kilometers per second, that means it's something that's really something from the space. But you get the phenomenon. It's not meteor showers, but when a satellite enters the atmosphere, or the Mir station 20 years ago, or any artificial human-made stuff enters the atmosphere, that makes like a big re-entry. It looks like a meteor, which is very slow, very big, but it makes the same phenomenon.
Yes, I'm sure. Like I think yesterday, this collection module from Hayabusa spacecraft came in with some matter from a from an asteroid. It landed in Australia. I'm sure some people must have meteorite photographs. What about this big fireball across the Japanese skies? That's been making a lot of news.
Yeah, the thing is that, as we said to Japanese media, this one was we've been calculating for me, because I must admit the last week was very busy. I didn't have a very big attention to the news. From what I saw a few days ago, so just 24, 48 hours after the fireball, it goes very fast. It's too fast. A big fireball, if you wanted to make meteorites possible in the end, it should not enter the atmosphere too fast. Because if it goes too fast, even if it's big, it's going to melt completely. So it needs to go slowly. And even the angle, if it goes straight, nearly vertical to the ground, that means the atmospheric path will be much shorter than it's something which is much horizontal. So depending on the angle entry, it's going to melt more or less. And from what I see with the video, it goes very fast. And in the end, it looks like there is very, very bright flash. That means it must have exploded. For me, it's fast with explosion. I'm not sure. I'm not that confident in the meteorite recovery. And the other issue, which is more physical, is that Japan is an island. So there are more chances that it falls in the water than it falls on the ground.
Sure.
But that's very logical. But it's a bright one. There were 3 bright fireballs in the past. So it's not something exceptional. most of the time people see this fireball was moon around the full moon brightness, the estimations. It's not exceptional, which is some you can observe on the Earth. There are many of them every day. Maybe not every day, but every week. Most of them are not seen because they are above the oceans. Most of them are not seen because they are above the deserts. So when they are observed above big cities, big populated cities, they think it's exceptional. It's not. It's been observed. But you've got many of them which are happening every day, every time. And one example is that there were 3 of them this summer in Japan. So nothing is happening with Japan. Everything's going to be okay. It's just they are lucky to have 3 fireballs visible from big cities. Okay. And for the meteorite recovery in July, they managed to get some because there was the meteor was smaller, not smaller, but it goes slower than the one we've been observing last week. So for me, it's too fast to get the meteor. But I may be wrong. I may be wrong because I did not get the real data. But it's too fast to get easy recovery of the meteorite.
Yes, but we all, of course, understand that if any of us have gone out and seen a meteor shower, the slower and the more angled ones are the most beautiful ones, and the ones to remember.
Hey, we got one over the nether because it's the extreme case, but it's very, very interesting. And there's a post, if you have a look at on the IMO website, there was one. It was in September or end of August above the Netherlands, which skipped the Earth. So it enters. It was nearly horizontal. It goes down and then bounced back into space. And we got the chance we have in Europe is that we got a big camera, big video network. So we were able to trace back the altitude, and you see the altitude of the object is going down and then going up. So that means it really bounced back to the Earth, to space, and that happens sometimes. It's the extreme case, but it's really interesting to see.
Wow, that's unbelievable, but it happens. So that's it's good that you could observe it, and I think I'll stress the point here that you're making is that if there is a good observations or observers network, then all these rare things can be captured, and of course we'll have a lot of data about the regular showers.
Yeah.
So definitely all the people who are here should listen to this, and if you're willing to form a group, let us know. We'll be there to help you out.
Yeah.
And
if people want, I don't know, in India wants to make a network, a video network, or just contact us because we got the experience on that. And especially in the US, even in Brazil, in Europe, there are many networks that's been built. So we will be able to give you the tips to be sure you make something which is useful, just in terms of density of camera repartition, because you sometimes don't need to put that many cameras when you've got something like a flat country. So if you want to build one, there are many. For the last 20 years, there are many networks that's been built and use this experience because we've been making mistakes. And so it would be a pity to make them again. So if some people are interested in making video networks, because today it's really working well, just ask us. We'll be happy to help.
Excellent. And that actually, I'll inform people a little later that next week we have a talk by about a project which is called the CAMS project. So Cameras for All Sky Meteor Survey, and Dr. Peter Jeniskens would be giving that talk at 11 next Sunday. And that is
he's the person who's going to be able to help you on that point.
Yes. So he'll tell you all about how to yourself make a CAMS network and do these observations. Excellent. So good that you led us to that information. Well, I will also say that the IMO website is a big treasure trove and people should visit it. Karl has already shown us something, but all these, like, even if you want some nice videos and records of meteors, they are there. And I just love the pictures also in general. So just continuing on the observations part. So I think because our focus of all these activities from IUCA is to get people to observe more. So there are a few questions related to that. One question is that from Bhavesh Rajput. It might be technical, but he asks, can we do spectroscopic observations of meteors, bright
Yeah.
ones?
It's good you got Peter Jeniskens next week, because he's been trying to do some. It's very complicated.
Okay.
Just because you can't predict where a meteor will occur. And most of the time, if you want to have some accurate spectroscopy, you need to get something like an instrument. So you have to observe a very small part of the sky and just pray to be sure something will come in the field. And it's not that easy. You can have some rough spectroscopy with whole sky cameras, but the spectrum won't be as accurate than with an instrument. And the issue with this domain is the luck. Just you need to be very lucky to get one going in the field. And I remember because there was a French scientist working with Jeniskens on these spectra, and he said that was awful. Just because you're looking at the part of the sky, you won't get a spectra and you see meteors all around the field, just like Murphy's law. It's always the case. If one day you photograph meteors, just be sure you're very calm, very peace, very quiet, because meteors will go everywhere in the sky except in the field of your camera. So for spectroscopy, the same. And the issue, you can do that because it gives information on two things: the atmosphere, because it's an atmospheric phenomenon. We must remember that. And also the rock stuff itself, because as it melts, in the light that is emitted, there are some parts which are due to the atmosphere and some which are due to the meteoroid itself. And what we see when we make some studies on that is that depending on the altitude of the meteor and depending on its speed, depending on its origin, we don't have the same spectra. There are some which are sodium, there's a lack of sodium, some which got some iron inside. And we see that depending on the origin and the altitude of the meteor, they don't have the same spectroscopic specificity.
Okay.
So it's possible, it's interesting, but you have to know it's hard.
Right, yeah, that's true. So there's also a question. I know that there are various kinds of audience here. So one person had asked if there is a telescope available through which you can watch a meteor or a meteor shower. So of course, you can't really track meteors with telescopes. And as you said, spectroscopic data is also difficult to come by because of that. How about photography? So it's are you recommending photography of showers as any a way of collecting data?
Yeah, you can do that. But now, in the past, we used to do that. That was the only way we had to get some very accurate path of meteors. Because when we have to, it's very important to this notion of radiant of the meteor shower is very important. Because in this data, you get the orbit of the meteor. So the more accurate you got the radiant position, the more accurate you got the orbit parameters of the meteoroids, so of the parent body of these meteoroids. So it's very important to know exactly where the radiant is positioned, and if it's a very narrow one, which means every meteoroid got nearly the same parallel trajectory, or if it's a broad one, because it's not a real point. Because if it's a point, that means every dust particles got exactly the same orbit. And it's never the case, because you've got some perturbations. So that means they are nearly parallel, but they are not exactly. And the more wide it is, the less parallelity there is between the particles. So to know exactly where the meteors come from is very important for us. And to know that, we need to get some very accurate path, apparent path. Because as I said, when you see a meteor, for you, it's going to be north. For someone which is more north, he will see it south. So everybody sees the meteor differently depending on where it's located relative to the meteor itself. And to get this very accurate path is the only way to get the exact position of the radiant. And in the past, the best way to get that was photography. Now, video is better because it gives the same information, but at the same time, you got the speed, you got the light curve, you got many more information. But if you picture a meteor, it's interesting for us. You can share the picture. I didn't say that, but every picture, every video of a meteor you have, you can share it on the IMO website. Mm-hmm. And we can get it in case we're interested in studying it, we can.
Okay. And So there's a curious student who's asking about the colors of meteors, and are you also recording them, and are they important?
Yeah,
Yes.
we are recording them just for information, because what we see most of the time, when you make a meteor session, when you make an observation of the Gemini next week, you will see dozens of meteors, hundreds of meteors. You will only see colors or guess colors for the brightest ones. And when you record your data, we ask you if you can say the colors of your meteor if you see some. From experience, because most of the time you see colors when the meteor is bright, and we have some observation of fireballs. And from there's a factory when you send data, which is what we call in French the fucking human factory. And this factory is very important for us to interpret the data, because when you see some data about fireballs, just for the brightness, some people will tell you it's -4, some other it's going to tell you it's -20 for the same object. So there's a very, very wide, because you'll speak to everyday people, some which are not used to estimate brightness. And what we realize by making these studies is that, for example, the brightness of a meteor is something you can't rely on when you take the testimonies, the witness. So most of the time we do not take this into account. If we don't have a video showing the meteor, we will never say, okay, someone's been watching something which was as bright as the full moon, it must be as bright as the full moon. Because I've been observing some which were maybe -5, -6, so it's not very bright fireballs. And I saw some witnesses who said it was brighter than the full moon for the same object, and it's not possible. Right. So it's something, and it's the brightness. For the color, it's even worse. Some people will see it red, some other will see it blue, and for many parameters, just because everybody does not have the same eyes. Right. So depending on your eyes, you will see different colors. Right. Depending on how aware if you were observing the sky, you were maybe more accurate than if you were just looking at the ground and was attracted by the light coming from the sky. And there are some very funny things. I got a friend who's been observing from a car, and he said, okay, it was just a very big green fireball. And a few weeks later, you realize that there was the window of the car was tainted. So the color was not coming from meteor, but just from the window. And there are many people watching a big fireball from windows. So there are many parameters that makes the color of the meteor very, very, very difficult to interpret. And even if you video photograph it, if you are a photographer, you know the colors of your photography is not the real one. Right. So if you do not make a spectroscopy, you will never be sure that the color you recorded, whether with your eyes or with the camera, will be the real one. Okay. So it's very complicated. We ask it because it can be some interesting values in some places, but we do not rely on that too. Except if there's something which is very universal. Everybody has been seeing it's red, okay, it must have been red. But most of the time, it's not a very important data for us. Okay. There's one thing to record when you see a meteor, whether it's very bright or not. It's the trajectory, the apparent path. It's the only thing which is very. If you just want data to record, is this one, because it's the one which will help you to build the trajectory and to know if it belongs to the shower or not, or if that will direct you to the meteorite or not. Okay. That's good to know. I mean, that's quite different. Yeah, it's not the more interesting data, because sometimes people, it was red. I say, okay, what's the trajectory? No, but it was red. Yes. But did you record the trajectory? No, but it was red. Okay, so it's not useful for us. I'm sorry for that. It's not useful. Sure. No, it's a good thing. Red, okay, but if you don't have the trajectory, we won't be able to make any more research on that. Sure. No, we understand, and thanks for sharing that. In fact. Well, so I think I'm sure like the people here are taking tips on what is a good observation, what is just looking and enjoying, but something else counts as a good piece of observation. So hopefully we'll take efforts to that. And in the future also we hope to have some training sessions
maybe not so early, but today evening we have a training session coming up. So I'll come to that. I'll just maybe I'll take one last good question, which asks us that is there a way to observe meteors in the daytime as well? Because some of the shower peaks come in the daytime, and then of course you can't see them with your eyes. But is there any other way which you could maybe observe or give some data?
That's a very good point. Is that when we look at the data, not the visual one with the naked eye, because unfortunately we are not accurate enough. And if you start observing, you will realize that sometimes you see 3 meteors that seems to come from the same region of the sky. And you say, okay, I've been discovering a new meteor shower, it's not. It's very complicated with naked eye, just because you're not accurate enough to be sure it comes from the same point of the sky. And you just see it once. So maybe it will, sometimes it happens in 15 minutes, you see 4 meteors coming from one point. You say, okay, maybe there was a meteor shower happening here, a very short one. It's possibility, it's maybe, but it can be chance too. And it's not possible to know because you're alone and you just see 4 meteors coming from the same region of the sky, which is not the case with videos recordings, which are much more accurate, which last all over the night. And if, for example, if I see some activity from from France, we can guess for 10 minutes, we see some activity coming from a region of the sky in Gemini in August. So it's something which is not usual. And at the same time, you see the same in Sweden. And then you see the same on all the places that are in the night sky at the same time. That means you really have been observing something that lasted 10 minutes. It was very short, but it's real. Okay. Naked eye, it's more complicated to confirm it's a real activity. But with the video today, we are detecting more and more very small meteor showers, which are maybe 2 meteors per hour. So it's very small. You won't go out at night just to observe that. Or you can, but it's just for scientific data more than for pleasure. Okay. And but we are discovering more and more. But difficulty is that you realize there are, I don't check, but if you have a look at the weekly meteor outlook on the IMO website, you will see that today we are speaking of the Geminis, but at the same time there are maybe 10 other small meteor showers that are active. That will maybe make 1 or 2 meteor per hour, but there are many other meteor showers which we detect and follow more easily with video recordings than visual ones. Okay, great. So it's great to know that radio too. Yes. So I think there are ways of discovering new meteor showers as well. That is very interesting to know. And I mean, so the discovery potential is always something which drives us to do more observations. So everybody, please note there is this great chance that you might just discover a new shower. So thank you, Karl. I'll just take a few moments away from your spotlight, and I'll inform people about the next few sessions that are coming up. And so let me share the screen and show the poster for that. So hopefully you are all seeing this. Just a moment. So I hope everybody's able to see this. So the next talk is going to be on CAMS, the Cameras for All Skies survey, meteor survey, and it's next Sunday, 11 a.m. So you can after that go to sleep and prepare for your next what do you call the your observation session for the night, basically. So that is there. And then we also have today evening a special session about researching the solar system. So this is a special session about the next meteor shower which is coming up. And if you want to basically watch the shower and take good observations of it, so you should practice. Now this is very important to practice. And I always stress that if you do good practice, you will end up with better results. So
So therefore, you can go for this talk. In fact, it's a live interaction session by Mr. Arvind Paranspe from the Nehru Planetarium here, and you will get hints at basically how to see the meteors and how you can actually find out whether they are meteor shower meteors or they are meteors which are sporadic, like they come from any side of the sky. So that is there, and in fact I would like to invite in Mr. Arvind Paranspe, who's doing the session later. He's director at the Nehru Planetarium. So he's here in the audience, and I will stop the sharing and invite him in for speaking for a few minutes, maybe on how to observe, on his experiences, and maybe on how to observe the Geminids. So Arvind, may I request you to come in, please? Are you around? Excellent. Welcome. I'm just asking you to unmute. One moment, please.
Yeah, I'm unmuted now.
Yes.
Can you hear me?
Yeah, I can hear you.
Before I say something, I also have a question to Karl, and that is, for some time we have been talking about the radio component. That is, this meteor, I suppose they go and ionize the upper atmosphere. So suppose, say between Mumbai and Pune, or stations which are within about 100-150 kilometers, there are a large number of FM radio stations which are transmitting. So suppose if what I do is, using my mobile camera, I tune it to a station which is not local, and I just leave it on. And in case there is a meteor up there in the sky, this I'm talking about doing it during the daytime. And if there is a meteor, I should immediately see a signal. So if I keep recording the radio station continuously, I don't even have to be present at that point in time. I just simply record it, and then I play back and see. I mean, we'll need to try this thing out, but this is something which I thought I'll ask you, and then probably propose this evening. So
yes,
you thought, yeah.
I did not get too far in this, but there are 4 ways to observe meteors. Visual, which can be video or naked eye. You've got telescopic, which is not this kind of visual, and you've got the radio or radar. And this is interesting because, as you said, it's something that it's more technical compared to so people who are easy with electronics, something like that, can build themselves their receptor and get this. But it's something which is very interesting because the ionized path of the meteor makes like a mirror for the radio waves, and that makes that you can detect a faraway transmitter. You should not get some emission by a direct way, but it goes up in the atmosphere, reflects on the meteor, and goes down. So that makes some kind of strange sounds, just like some things or I make a meteor simulation. So like this, you can record meteors all night and all day long, and even when it's cloudy. So it's one of the best way to know the meteor activity 24 hours on 24/1, 7 days on 7 days when your material is working. And that's also a good point to detect some meteor showers. So we were discussing some meteor shower discoveries. Video allows to discover a lot, radio too. And there's a big radio and radar network in Canada and the US, and which is making that. You can have a look at the data. It's called CMOR. And you've got the meteor activity in real time, and you see the different radiant active. And when there's an outburst, that suddenly a meteor shower, which is unknown, is very active, you can see it on that. And it's a very good way. It's more technical. That means someone which is not very at ease with technical stuff and electronics and things like that may have a bit of difficulty, but it's a very, very good way to study meteors today and activity, especially activity.
Thank you. Thank you.
Welcome.
Yes, thanks. So sun is up behind you.
Sorry?
Sun has come behind you. We see a background light.
Yeah, yeah, the sun has come. It was the dark at the very beginning, and now sun is rising in France.
Okay. So friends, in the evening at 6 o'clock, as Samir has said, we have a Digistar 6 planetarium software. And Karl also had said that there are some simulation software available, which you can simulate a meteor shower. So what I will be doing is that I will use one of these simulating software, that is the Digistar 6 software, and generate artificial Geminite shower. You will realize that when we say that it is 150 meteors per hour, what it means is one meteor every 30 seconds, but how long that time is. So in order for us to get prepared, we will do that. Also, there have been many groups in India which they have been observing meteor showers. So based on our experience, I will share those points with all of you, so that as Karl has been talking about, you can fruitfully contribute to the international database of meteor observations. And also not get very disappointed, because many times when you see something in the newspaper, a big thing happening, and people come, and then you go out and try and see meteor shower, and you don't see as many meteors as you expected. But if you actually play by the rule, that is, you take as he said, take a proper sleep, keep yourself warm, and then it is a very enjoyable experience. From IMO site, their annual calendar, it tells us that the Geminids are expected to peak at about 6:30 Indian time. So best time for us to see is that after about 1 o'clock or so, early in the morning, and then as day breaks. So we will talk about that.
Mm-hmm.
Yeah. Okay. Right.
Okay, yeah, that's good. Yeah, so you're welcome. Just if anyone in the audience got any question and was too shy to ask it right now, just send us an email. There's a question email on the IMO website, which is info@imo.net. Just send your question and we'll answer it, or we will direct it to the good person. But it can be very technical, can be very simple question, just ask them. We'll be happy to answer. Yeah. Mm. Okay. Mm. Yeah. We all have. Yeah. You're welcome. Yes. All right. Okay. Waiting for your reports and your data. So, thanks for inviting us. That was great. Great plan. Okay. Bye.